This is video number 5 in our series, the SuperPowerful Vector Identities technique. What we're going to do in this video is have a workout, so to speak, with the scalar triple product, and also in the next video as well. And then after that, we'll have the background to explain what this equation means and actually prove it. And then once we do that, we will use this as a very powerful tool to solve complicated vector identity problems. It takes a while to get used to the technique, so we're trying to take our time and lay out the foundation here, but it's very powerful, very well worth learning. Also, it sort of gets one in the mindset of how to manipulate symbols in sort of an abstract setting, and that's the kind of background that helps you work with tensors as well. But for this video, we want to consider the scalar triple product. So say we have vectors A, B, and C. What we want to do is show that the triple scalar product for these can be expressed like this. Now you're probably used to seeing it in this form. It's expressed as this determinant, A, B, C, A, B, C, expanded out using minors, and we get this expression. And of course it is a scalar product because we are indeed taking the dot product of two vectors. B cross C gives us a vector that's perpendicular to both of these, and we're taking the dot product of that vector with vector A, which of course gives us a scalar expression. Now, back in the very first video, we had again laid out just a basic foundation concerning the Kronecker delta product, where if we have two vectors, say x and y, expressed like this with their repeated indexes, then the dot product can be expressed in component form like this, which takes us to this expression with the repeated indexes, which means we sum over it from 1 to 3, as we did in the very first video, to give us this expression. So this is how we write the dot product then in component form. And then in video number 2, we showed that the determinant of a matrix can be expressed using the permutation symbol. And then in videos 3 and 4, we worked with the cross product and the permutation symbol. Now we're going to work with the scalar triple product and the permutation symbol. Now again, just to remind ourselves, say that we are going to take the dot product of vector A with another vector, we'll call it Z. And to express that in component form, we could just say, well, it would be an ith component of A times an ith component of Z. We have repeated indexes, so we sum over it, just like we did in the very first video. That gives us this expression for our dot product. Well, here we want to take the dot product of A and B cross C, so let's write this out in component form. A dot B cross C, that would be an ith component of A times an ith component of vector B cross C, just like we did with vector A and vector Z, exactly the same process. But what is an ith component for B cross C? Remember now sort of the generic formula for our cross product. A cross B equals epsilon AB. The order is important now. A, B, and we're going to have a unit vector here. Now, A we were expressing with an I index, B with a J index. So we have I here, J here, and this was EK. You can think of this as sort of like, this is like the leftover letter that goes on here, because we have only 3 orthogonal unit vectors, E1, E2, and E3, or I, J, K. So to help you remember, you can say, well, we use the I, we use the J, K is the only letter that's left over for our unit vector. Again, we didn't derive it like that. We formally derived it, but to help us remember, we can think of it in those terms. Well, here we have B cross C. So it's going to be an analogous process. This will equal, this has to be I, J, K. The order of these indexes here have to match. Now for B cross C, let's make some more room for it. Same process. We need an epsilon, BC, BC, and some unit vector. B, we had a J index, and C, we had a K index. So C, K, the leftover letter, to think of it in those terms, is I. So this is J, K, I. So this is B cross C in component form using the permutation symbol. But we want the ith component of that vector B cross C. But of course, the ith component of it, I should say an ith component of it, that's just equal to the vector B cross C, then take the dot product of it with a unit vector EI. But this is this. So this equals epsilon J K I B sub J C sub K EI. That is B cross C. And we need to take the dot product of this with EI. Of course, EI dot EI is just 1, so we have that. And again, we also did this in video number 3, I believe it was, so hopefully this is familiar news. This equals then epsilon JKI B sub J C sub K. Now, let's go back to where we started then. We were writing out the dot product in component form. Now for this, we can substitute this, epsilon JKI B sub J C sub K. So let's put this in place of this. Now we get rid of this. And we substitute in epsilon J K I B sub J C sub K. Okay, now what are we doing here? We have 3 different sets of scalars, A, B, and C. We have repeated indexes, so we're never going to be multiplying and adding them. The order in which we do it doesn't matter. The order in which you multiply and add scalars is irrelevant. So we can move this inside of here, but we had to do it so that once we move it inside, that all the indexes match. So if I was going to put this to the inside here, we'd move it over in this position. J, K, I. And we're going to write more on this line, so let's move this over to here. So we have epsilon J, K, I, B, J, C, K, A, I. Now, remember from, I think it was video number 3, we established that all of these here have a value of +1. This is like our prototypical sequence, and these here are even permutations of that. So epsilon jki is equal to epsilon ijk, and here we have jki. So we could say, well, we could also write this as epsilon ijk. But if we do that, we have to shuffle these around so that these indexes match. And we can shuffle these around. That's valid because these are just scalars, and all they're doing is multiplying scalars together. The order in which we do it is irrelevant. So this expression is equal to this expression. So finally then we have that A dot B cross C equals epsilon ijk A B C I J K. And there then we have expressed this, the scalar triple product using our permutation symbol. Now we could express it like this too. That's perfectly valid. But in all of our vector expressions, we try to have it set up so we have epsilon ijk. But again, as we stated now at the beginning part of the video, you're probably used to seeing that written out in determinate form. If we can find our demonstration sheet like this. And then when we expand out in minors, we get this expression. Well, if this is a true expression, if we expand this out by summing over our repeated indexes, it should give us this. So let's just take a few moments and go through that process and see what it generates. That here we have it right here. So let's just erase the whiteboard. And here we have epsilon ijk, ai, bj, ck. I is repeated, j is repeated, k is repeated. We sum over all of them. So first we'll sum over the I. So I goes from 1 to 3. So here we have I is 1, I is 2, I is 3. Now do it for j. J is 1, but that gives us a repeated index here, so that's 0. J is 2. And then we have it right here. Then j is 3. We have that right here. Then on to this term. J is 1, right here. J is 2, repeated index, that's 0. J is 3, that gives us right here. Then we go on to this term. J is 1, there's J is 1, J is 2, J is 2, J is 3, we have a repeated index, that is 0. Just like here when J was 2, that gave us a repeated index, so that was 0. So we have these 6 terms. Now we sum over the k's. K is 1, that's a repeated index, that's 0. K is 2, another repeated index, that's 0. K is 3. So that gives us this term right here. Then for here, the only non-zero term we get is when K is equal to 2. That's that term right here. The only non-repeating index we get, the only non-zero term we get, is when K equals 3. That's that term. For here, K has to be 1. That is this term. K has to be 2. That is this term. K has to be 1. That is this term. So here's what we end up with. And remember from video number 2, epsilon 1, 2, 3, that's positive. Epsilon 1, 3, 2, that's an odd permutation of this, that's negative. Likewise, this is negative. This is an odd permutation. 2, 3, 1, that's an even permutation, so that's positive. 3, 1, 2, that's an even permutation, that's positive. 3, 2, 1, that's an odd permutation, this is negative. And again, we went through that in more detail in our second video. But let's look what we have then. Here we have A1, B2, C3 minus A1, B3, C2. Let's factor out the A1. We have B2, C3 minus B3, C2. And that's what we have right here. B2, C3 minus B3, C2 times A1. Then here we have A2, negative A2, B1, C3, plus A2, B3, C1. Factor out the A2, we'll have B3, C1 minus B1, C3. And that is written down right here. And here we have A3 is common to these. This is plus, this is minus, so we'll have A3, B1, C2 minus B2, C1. That is right here. Now, how do these compare with these that we got from our determinant form for the scalar triple product, expanding it out with minors? So you have A1, B2, C3. Let's see if we can get these together simultaneously. B2, C3, B2, C3 minus B3, C2. Now here we have minus sign here, so this would be plus B3, C1. B3, C1 minus B1, C3 minus B1, C3 times A2. And for A3, B1, C2, B1, C2 minus B2, C1, they come out the same. So what we have shown then is our scalar triple product in permutation form we can express like this. A dot B cross C equals epsilon A B C I J K I J K. In component form, vector A is this. Vector B, remember we had like this. And vector C, we had like this. And there is the scalar triple product. Okay, I think we're going to end the video here. In the next video, we're going to prove a vector identity of the scalar triple product, making use of this equation. So that will come up in the next video. I think that will be video number 6. Anyway, the playlist for our vector analysis series, the playlist for the videos is at the website digital-university.org.